Another day in DC means another day at the 2018 AGU Fall meeting. There's lots of coverage coming your way. AGU TV starts now. Hello and welcome to day 3 of AGU TV. I'm your host, Stephen Hall. What an exciting first few days it's been, hasn't it? There's almost 28,000 of us here in Washington, DC, but don't worry, we're not even close to winding up just yet. Today we're stopping by a panel on sexual harassment prevention. We're interviewing newsmakers and we're touring top universities and organizations doing cutting-edge work in science. Absolutely delighted now to be joined by Kristie Ebi. Chris, welcome.
Thank you, it's good to be here.
Thank you very much indeed for taking the time to talk to us today.
My pleasure.
So, National Climate Assessment Reports. What is a National Climate Assessment Report and why is it important?
The National Climate Assessments are mandated by law. Congress passed a law in 1990 saying that every 4 years there needs to be an assessment of what we know in the United States about the state of climate science, what's happened in the United States in terms of impacts of a changing climate, what the risks are for the future, and what can we do about it? Are there ways that we can reduce our risks in the short and the long term?
So the last report that you did, what were some of the findings?
Some of the key findings in the 4th report are that we all know that the climate is changing. It's become much clearer over the last 4 years that these changes have resulted in impacts on our health, on our livelihoods, and our ecosystems. So we can now document impacts of a changing climate in the United States and clearly show that each additional unit of warming will have higher risks. That is, we go from current warming, which is about 1 degree above pre-industrial, to 1.5 degrees Celsius to 2 degrees Celsius, that each increase is associated with greater risks. So it increases the urgency for reducing our greenhouse gas emissions and for increasing our adaptation, preparing our communities to manage the changes that are ongoing.
That sounds really important, doesn't it? Because you're actually saying that changes to the climate right now are affecting the health of communities here in the United States.
That's true. It is going on right now that people are suffering and dying from events related to a changing climate. And so it's urgent that we address those and be prepared for even further changes.
So you say it's urgent that we address them. How do we address them?
There's 2 main sets of policies that we use to address these. One is called adaptation. And adaptation is recognizing climate change is going on right now, increases in the frequency and intensity of extreme events. We've seen devastating consequences from wildfires, from hurricanes,
Sure.
And making sure that our communities are prepared to manage these changes as they come. Recognizing that many of these changes are compound changes.
Right.
So you look at California where you both had long-term drought and then you had wildfires. So you need to manage combinations of these risks. And so finding ways to ensure that we're ready. For health, for example, there's surveillance programs to tell us where mosquitoes and ticks are that carry diseases. Right. We need to know where they are. We need to track them as they change their ranges. We need to put in early warning systems to warn communities of when there are changes coming about. And in the longer term, we need to reduce our greenhouse gas emissions.
Right.
And a key message from the report is not that we just need to reduce our emissions, but that essentially all mitigation policies have health co-benefits.
Right.
And so it's good for our health to reduce emissions from power plants, reduce emissions from tailpipes, get more people out walking and biking. And those benefits to our health are now, so they'll happen much sooner than the benefits of mitigating greenhouse gases for our future climate. And when you estimate the costs associated with those benefits, when you estimate the value of reduced hospitalizations, reductions in premature mortality, that value is almost as much as the cost of mitigating itself. So we should be doing this now for our health.
I have to ask you though, you make the case that this is really important and people are suffering and in fact dying. You make the case for the benefits of taking action. I have to ask you though, do you think America is listening?
They're listening now more than they have before. There's been a series of reports that came out this fall, the Intergovernmental Panel on Climate Change Special Report, the National Climate Assessment, other documents have come out.
Right.
And the media attention has been very, very large. So it does seem as if people are now getting the message more clearly, and surveys suggest that more and more Americans are committed to making a difference.
Okay. Now my final question is, it's great that you do all this work, but it's voluntary work, isn't it? It's volunteers.
It's voluntary work. It's nights, it's weekends, it's family holidays. But we do it because we see the value of it, and we think it's important for the American public to know where we stand with respect to understanding about climate change.
Chris, thank you ever so much. Really
Thank you so much.
appreciate it.
Thank you.
Let's now start our tour of those very best scientific universities, institutions throughout the world. Let's begin today at Johns Hopkins.
The Department of Earth and Planetary Sciences was formed in 1968 as the result of a merger between the Geology and Oceanography departments at Johns Hopkins, one of the first departments of Earth and Planetary Science in the country. The department's three major areas of focus right now are the fluid dynamics of planetary systems, the history of the Earth, and the behavior of planets as systems, not just within the solar system, but even outside the solar system, including exoplanets. The concept of change is vital to the research because planets are dynamic systems. Different parts of the planets change over time, and those changes have impacts not only on the particular process that one is concerned with, but potential changes for the whole evolution of the system, including life itself. And we've hired a bunch of people in the last few years who also think in terms of planets as systems.
At Hopkins, we're working to understand both the modern and ancient climate of the planet Mars. In the past, we thought that most of the geological activity on Mars happened in the ancient past, and certainly a lot of it has. Using data from missions like the Curiosity rover, we've been able to show that the modern surface environment is much more dynamic than we had appreciated, and that sediment is moved frequently, both on daily and annual timescales. On Earth, the sedimentary rock record tells us all sorts of things about the history of our own planet, from plate tectonics to the evolution of life. On Mars, we used to think the surface and crust of the planet was dominated by volcanic rocks, but in the past 15 years or so, we've come to appreciate just how common sedimentary rocks are on the surface of Mars as well. In my lab, we've been using analysis of these rocks to help us understand what the ancient Martian past was like, and these rocks really give us a window into the ancient history of Mars, as well as the first billion years of solar system evolution.
So I am really interested in fossils, especially Ediacaran and Cambrian fossils. And I'm interested in periods of change. I'm interested in extinction events and radiation events. So I'm looking at these fossils in the context of environmental changes that are happening at the same time, before or after, and try to link the fossil record with other proxy records. And there are all these interesting environmental changes associated with these big shifts in life. One of the places where I do fieldwork is the Southwest US. About 5 years ago, we discovered some Ediacaran fossils. So Ediacaran fossils are incredibly rare. We discovered a range of shapes, a range of sizes, and so it launched this whole project, and now we're working on the taxonomy of these fossils, the paleo-environmental context of these fossils, and trying to link these fossils with different environmental proxy records.
In the case of deep rocks, which formed in environments that aren't directly observable, there has been sometimes a propensity towards interpretation of their formation and the processes they record as uniform rate and protracted. Work that colleagues of mine and I are doing is starting to suggest that these rocks and processes may include great non-uniformity in rates, such that what they record relates to their more memorable moments rather than their everyday experience. Punctuated equilibria refers to processes of evolution that proceed by rapid changes, punctuating periods of relative stasis. Concepts analogous to punctuated equilibrium may be applied to plate tectonics in terms of viewing tectonic processes as drawn-out, long time frame periods of dynamic equilibrium that are punctuated by plate reorganization events and relative tectonic upheaval. The question is then, how much of the rocks and landscapes that we see and interact with are formed as a result of these periods of tectonic upheaval and reorganization, as opposed to the periods of relative steady state typical conditions.
Ecologists have traditionally ignored cities, but they're actually the location where most humans interact with their environment and are dynamic ecosystems in their own right. And understanding the ecology of cities is key to meeting sustainability goals. Ecologists have a long history of doing ecosystem-level studies where we conceptualize systems as a whole. And by bringing this approach to cities, we can better plan cities for both the environment and future inhabitants. My research at CONS is really focused on how global change in general is going to affect plant communities and the resultant ecosystem services they provide. And I apply what I learn and understand from these more natural systems in tallgrass prairies to very managed and constructed communities here in cities. Ultimately, what we're trying to understand is if ecological theory holds up across very managed landscapes.
We're used to thinking about rock chemistry as reflecting the environment, but we're also learning that it may reflect the organisms that live in and modify the environment. So a major change that we're understanding in rock chemistry, and specifically in ocean chemistry in the past, is that rocks record local conditions as well as global conditions. Sometimes we like to look at the rock record and think that we're looking at secular variation in seawater chemistry, but sometimes they're recording local environmental signals. And the thing that's really exciting about that is that knowledge of both local and global processes is really necessary for us to understand how the environment changes and how it responds to things that might stress a system. So one thing that's really great about being at Johns Hopkins University is we're close to Chesapeake Bay. And Chesapeake Bay is an estuary that is economically important, but it's also home to a really large dead zone. Dead zones are places in the ocean where there's no oxygen in the water column. And we really want to understand how these dead zones are going to either expand or contract under future scenarios of warming, because that can affect fish and other things that live in the ocean, as well as ecosystem health.
So you've just seen a snapshot of the research that's going on in this building. It's changing our view of many, many systems from planets to ecosystems, and we look forward to seeing how that's going to develop in the next decades.
The 21st century is the century of ocean. However, ocean exploration and development is characterized by high technology, high risk, and high investment.
How to integrate the multi-channel information and how to coordinate multi-institutional infrastructure are the major challenges in ocean and climate science right now.
更需要我们全世界的科学家联合起来，共同协同攻关，来共同来认识海洋，来开发海洋，让海洋为人类造福。
The establishment of Marine National Lab was approved by China's Ministry of Science and Technology in 2013. Our national lab is in the best position to pursue synergy for ocean research through gathering resources at home and abroad. Qingdao National Laboratory for Marine Science and Technology focuses on advancing both fundamental and cutting-edge research by integrating resources and talent, forging partnership, and sharing major facilities worldwide. QNM is designed to cover nearly all marine disciplines. We have been working on issues such as ocean observation, resource utilization, and marine ecological environmental protection. To pursue solutions to those global challenges, we are leveraging the state-of-the-art technologies to support relevant research. QNM activity promotes the construction of the third ocean drilling vessel in the world, with the aim to break through the Earth's crust and enter the mantle. High Performance Computing Center provides technological support of computing science, artificial intelligence, and big data. QNM sets 4 types of research units: functional labs focusing on fundamental research, joint labs focusing on technologies, open studios invite teams worldwide to conduct projects, and overseas research centers for collaborative research.
We integrate resources and professional team all over China to conduct the research. The laboratory for marine mineral resource focus on 4 research fields: marine gas hydrate, oil and gas, solid minerals, and key technology for marine mineral detection. Our lab established this technical system for the gas hydrate in the water for the first time in 2017. Results has played an important role in the gas hydrate production test in China.
The functional laboratory for ocean and climate dynamics focuses on the structure, dynamics, and variability of oceanic processes in the coastal seas, the open and deep oceans associated with climate change and environmental change. For example, the temperature salinity, circulation, response, and feedback to climate variation in the China Seas and the Western Pacific. Interdisciplinary and collaborative research is essential in this lab since the scientific issues associated with climate change are so complicated and comprehensive.
We aim to build high-resolution Earth system model to simulate the environmental changes over the past 25,000 years with light of Taihu supercomputer through cross-disciplinary collaboration. The Infrastructure and Innovation Center for Marine Drug Screening and Evaluation in Kuala has united over 20 research teams from 5 countries including China, US, UK, France, and Spain. This is the first time in the world to screen active drug molecules in such a large scale. Qingdao is home to 30% of China's marine institutions, as well as 50% of its marine talents.
青岛海洋科学技术国家实验室位于中国青岛蓝谷黄海之滨。青岛蓝谷是一个以海洋为特色的高科技研发和高技术产业的聚集区。为了实现这个目标，我们集聚了中国最顶尖的海洋科技创新平台海洋国家实验室，也集聚了一批科研院所和产业。这样的话，打造了一个产学研相辅相成的一个创新生态体系。包括我们国外的科学家到这儿来跟国家实验室合作。
QNM has established a number of open infrastructures for marine research. Scientists worldwide can access such infrastructures as the world's fastest supercomputing center in marine field and the research vessel fleet to support their research. We highly value international collaboration. To facilitate a cooperation among the global marine community, we have held 2 rounds of Global Ocean Summit, gathering over 200 leaders of top marine institutions worldwide. To gather top scientists and engineers worldwide, we launched the Ocean Talent Program to provide the most enabling research environment for scientists. We are establishing overseas research centers with the world's best marine institutes, working with Australia's CSIRO. We launched the International Center for Southern Hemisphere Ocean Research. I'm looking forward to world-leading integrated marine research center to tackle the most pressing global challenges and conducting cutting-edge research for the benefit of humanity.
Marine environments are facing drastic changes in the future. To investigate the combined impact of climate change, natural variability, and human influences, the German Federal Ministry of Education and Research established the National Marine Research Program MARA-N, Coastal, Marine, and Polar Research for Sustainability in 2016, under the umbrella of the Research for Sustainable Development Framework Program. With its 6 interdisciplinary topics and 2 cross-sectional activities, MARA-N addresses all aspects of marine research.
MARA-N is a basic funding framework program of our ministry to fund coastal, marine and polar research activities. We provide to our excellent scientists state-of-the-art research infrastructure. For example, Germany has one of the most modern fleets for research vessels in the world. Institutional funding, as well as the project funding of marine research. And of course, our marine research activities are embedded in an international as well as European research agenda.
MARA-N research will support the implementation of both EU directives and the UN's 2030 Agenda for Sustainable Development. To deliver solutions for politics and society to protect and sustainably use our oceans in the future, the program supports several national and international marine research efforts, including the Regional Atlantic Circulation and Global Change Program, RACE.
Under global warming, the Atlantic circulation will change severely, and it will have grave impacts on the climate system and also on sea level in Western Europe, but also in North America. RACE maintains 5 long-term transport time series in key regions of the Atlantic circulation, and these enabled us for the first time to quantify the mean of the circulation. But we also found out that there is a large variability from days to even several years, which were unknown so far. We could also illuminate the vast progress which has been made in the realistic simulation of the Atlantic circulation. In typical climate models, this freshwater invading in the key region determines the strength of the Atlantic circulation. But in the Viking model, most of this freshwater stays in the boundary current around this key region, and only later into a very small fraction invades in the key region.
The Viking simulation was recently confirmed by observations measuring fresh water in the Labrador Sea. In addition to ocean research, MARA-N also supports studies into the impact of human and natural forces on our coastal regions, including the development of new protective measures for coasts worldwide.
The research programs by BMBF not just focus on fundamental research, but applied research. So what are the effects of waves and tidal currents on marine infrastructure, sediment entrainment and transport in coastal environments, ecosystem services of plants like salt marshes or seagrass meadows for the level of protection of coastlines. We deal with capacity building efforts that say the experiences and also technologies from Germany can be implemented in developing countries in order to sustain their future. We focused on the city of Padang that is on the shores of Sumatra. We looked into tsunami inundation and contrasted this, how the city needs to be evacuated due to an, say, incoming tsunami that will hit the city of Padang within 50 to 20 minutes.
Coastal dynamics are not only studied in temperate and tropical regions, but also in the Arctic, one of the least studied areas on Earth, including the impact of permafrost thaw on coastal Arctic waters. The permafrost thaw impacts the global climate and the Arctic Ocean. In September 2019, Mosaic, the largest Central Arctic expedition in the world, will be launched.
The Arctic region is one of the fastest warming regions of Earth. The losses of sea ice that we observe is not well predicted, not well described by our current Earth system models. And we suspect that the lack of observation, the lack of knowledge about the Arctic winter is a key problem. The Mosaic expedition is about setting up a multidisciplinary observatory for the study of Arctic climate. It means that we will freeze in our icebreaker Polarstern for a year to drift along with the sea ice across the North Pole. And we will host 600 scientists from 17 different countries to carry out studies about how the winter influences Arctic climate. And it's also a big logistical challenge. We need to make sure that 600 people are exchanged throughout the year. We need a runway on the ever-thinning sea ice. We need to provide fuel and food all of the time. And we need to make sure that everyone comes home safe.
Thanks to the hundreds of researchers involved in MARA-N studies and the vast amount of data collected, marine research in Germany will make a vital contribution to the discourse on our ocean's future with policymakers and the public around the globe.
In 2016, we started an open dialogue involving all the stakeholders, scientists, the representatives of civil organizations, business people, as well as governmental experts. And by this open dialogue, we tried to identify research fields relevant to all these stakeholders, but as well systemic solutions to the challenge of sustainable polar and marine research. Germany is very proud to support the United Nations Decade of Ocean Science for Sustainable Development from 2021 to 2030, and we are very proud to host the kick-off event in Germany.
The problem that scientists have had for a long time in the geosciences domain is gathering our information, sharing our information, and using it with each other in a way that was easy and maintained all the fidelity, all the information about the data. EarthCube was established in part as a way to help streamline the process for working scientists to acquire data, but also to help us look for relationships between different kinds of observations from different what we call science domains to better understand how nature works.
EarthCube is all about getting together three primary groups of domain scientists, computer scientists, and also the data people, data managers and data scientists.
The vision I like to use is equivalent to one of these home devices that I can speak to. For instance, I'd like to say, ooh, how do erupting volcanoes in this part of the world affect climate in that part of the world? And maybe no one's asked that question before, but by having access to all that information in a way that's interoperable, we can start to look for those sorts of relationships to understand if that question even has any meaning.
I love volcanoes. I study the East Africa Rift System. A part of my job is installing a volcano observatory there. So for us, we've partnered with an EarthCube project called CORDS. CORDS is the cloud-hosted real-time data for the geosciences. So we use this cyber tool, and what it does is all of the brunt work for us. It's able to take a data stream that's coming in from Tanzania, properly search the stream for the information that we require as geodesists, and then give us that information in a way that we can actually do something with it. So in CORD's case, that would be automatic plotting and or automatic downloads.
These tools are allowing us to access data and work with it in ways that we wouldn't have been able to do as easily before. And I'm seeing a shift in these early career researchers, that they're becoming a lot more open to the next level of cyber infrastructure. And I think EarthCube represents one aspect of the next level of cyber infrastructure for geosciences.
Another really interesting application is an application called Flyover Country.
Flyover Country brings information about the landscapes around you to your phone, no matter if you have a connection or not. So it can be while you're flying in an airplane, looking at the airplane window, or on a road trip, driving along, or on a hike up in the mountains. You can pull up information about the landscape sourced from many different geoscience databases and have some access to what scientists have learned about the landscape that you're currently encountering. That EarthCube concept of making data accessible and available easily in formats that allow people to work with it made it actually possible to make an app like that.
EarthCube's commitment to making all of its code and software open source is very exciting. EarthCube is also adopting fair data principles, making data findable, accessible, interoperable, and reusable. And data sharing means that you get new collaborators, and it means that your work goes further than it would before, and it means that the study that you did can be reused in a larger context in many other places. So that means a lot for the future of science and the future of collaboration.
That's where I see the future of geosciences data going. People sharing when they publish their data, not just the paper, not just the data that goes with the paper, but the workflow that got to the place of analysis that you're publishing.
EarthCube is part of a data revolution and a cyber infrastructure revolution that is happening in our discipline to provide the rest of the geosciences community infrastructure and a roadmap for optimization of all of the work that we do and how we conduct our research into the future, how we record our research, and how we present it to other people.
This EarthCube community, I would say, is really more to sound very sappy, a family, where people are spread out over different universities, different research consortiums, and they are working together to share science.
I think the communication of science is like one of the ultimate goals of it is to bring the knowledge of the wonderful stories of the ways that the world has come to be, that the way it is, to people.
EarthCube is a realization of a dream, the dream to take the latest cutting-edge technology and apply it to science workflows for meaningful results.
I am convening a panel on sexual harassment in the sciences and what we can do about it. It's a union session. This topic impacts the entire fabric of our science. It's a real problem in our science, and AGU is ahead of the curve in bringing these experts together from around the globe to talk about what's the evidence for it and what are the solutions. AGU started to address this issue before the Me Too movement, but almost at the same time the Me Too movement erupted, it became very clear that this problem was one we needed to address. So a National Academy panel report came out this year that demonstrated that science is one of the worst places for women to work, and we are trying to make it one of the best places for women to work. Our members are asking what they can do about it, and some people are still asking for what's the evidence that it's a problem in our community. So this panel will help educate and inform and provide topics for everybody to discuss on why it's happening and what we can do about it and how we can make science a good place for people to work. I hope people walk away understanding what the evidence is that this is a problem based on data, and being able to talk about what are the solutions for us to address this problem.
What a pleasure to be joined by Rebecca French now. Rebecca, welcome.
Thank you.
Thank you very much indeed for joining us today.
Pleasure.
Really appreciate it. So how important is it that communities throughout the United States, when they're making decisions, they understand the science on climate change?
It's incredibly important. I am the Director of Resilience for the State of Connecticut Department of Housing, and in my role there, I've been charged with helping communities adapt to the impacts of climate change they're already feeling in the state of Connecticut, as well as recovering from past storms. We're still in a recovery process from Tropical Storm Irene and Sandy, so I have to translate that climate information directly to state and local decision making.
What are some of the practical things that communities can and need to do?
Well, this is a highly practical issue when it comes to adaptation to climate change. Municipalities are seeing, particularly roads near the coast, are flooding on a more frequent basis. They flood during storms. Sometimes they flood during high tide. So this is an impact they're already feeling. People are driving through this, their feet are wet already, so they absolutely have to take action on this issue. And the questions they're coming to myself as a translator of climate science information and sea level rise is, how high should I elevate this road? Where do I move my infrastructure? How do we take that national information that I see on the news, I see coming out of conferences like AGU, and take that down to a highly localized decision of I have Route 146 that floods 3 times a month. What do I do about that?
It's something we've been talking about all week, really, which is you have all this science going on. How important is it that the science community actually communicates in such a way that people outside of that community can make sense of what they're saying?
Well, I think there's different scales for this, right? So I've worked in federal and state policy. So I think it's incredibly important to talk to Congress about the big issues that are coming out of the climate science so that resources flow towards these problems. Being in the state government now, where I'm a recipient of those resources on behalf of the state of Connecticut, I'm looking to scientists who can take their information and again put it to a highly local issue. And that's not always possible. That's a challenge that we're continuing to address, I think, here at AGU, as we've had some luck with being able to translate sea level rise information, at least between now and the year 2050. But it's a much more difficult question when I get asked about precipitation, because it's highly variable across the state. So how can I tell someone what exactly they should be preparing for?
How much of a recognition in your work, in policy work, in a federal at a state level, do you get in terms of what we can actually do about climate change as opposed to adapting for the consequences of it?
Well, again, I'm speaking from my experience in the state of Connecticut. We're a highly active state on addressing both the carbon emissions side as well as the adaptation. We've set very stringent standards for reducing our emissions. Just passed a new law for a 45% reduction in the near term. So Connecticut is acting on both fronts. In fact, I would say we've been much more active on the energy side, and we're starting to, since Sandy and Irene, that's kind of kicked off thinking about, oh, wait a minute, we've actually also already baked in impacts that we also have to address.
Okay. Well, thank you very much indeed for joining us today. Fascinating discussion. Thank you.
Thank you for having me.
Rapid decrease in Arctic snow and ice and significant environmental changes are the most drastic evidence of global warming. Better understanding of the status and trend and causes of Arctic environmental changes and accurate future prediction are very important, not only for Arctic but also global climate issues. JAMSTEC have been conducting the Arctic research since early 1990s. Then, with accumulating our experience for the Arctic research and also in the context of growing social interest of Arctic issues, JAMSTEC established the Institute of Arctic Climate and Environmental Research, so-called IACE, on April 1st, 2015. We are now investigating Arctic environmental changes using research vessel Mirai, Earth simulator, and other facilities. Research vessel Mirai has been conducting the Arctic Ocean observation cruise almost every year since 1998. Our research target is mainly in sea ice reduction area to understand what kind of changes and impacts can be found after sea ice retreating land. We found that due to global warming and sea ice reduction, the Arctic Ocean is warming, freshening, and changing more active. Also, it was a very cold and quiet ocean with sea ice cover. We also understand that, especially in the Pacific sector of the Arctic Ocean, influence of Pacific water inflow through the Bering Strait are very important from not only physical and chemical, but also biological points of view. To evaluate the impact of the Arctic environmental stressors on marine organisms and ecosystems in lower trophic level, we have conducted field observation, plankton culture experiment, and development of numerical modeling. Ocean acidification is proceeding in the Arctic with the fastest rate of the world due to sea ice reduction and increase in freshwater input. Micro X-ray computer tomography technique is one of the useful methods for ocean acidification research. Using this technique and collected samples from the Arctic Ocean, we can evaluate the change of carbonate shell density of planktic foraminifera and theropod dwelling under the condition of ongoing ocean acidification. In this research unit, we also started collaboration with ocean policy experts for further research on marine ecosystems and educational outreach activities. Temperatures have been increasing at higher rate in the northern high latitudes, especially over the land area. This can greatly alter the atmosphere and the terrestrial surface environment, such as permafrost degradation, wildfire, and greenhouse gas emissions from boreal forest ecosystems. We are trying to understand the impact of Arctic warming in a long-term flagship observing site in interior Alaska. The vertical, turbulent greenhouse gas fluxes between the atmosphere and the surface are measured by the eddy covariance method. We are also measuring and modeling the black carbon emission, transport, and deposition. They are also an important topic for the understanding of the role of black carbon to climate feedbacks.
Our group performed numerical experiments in order to elucidate how the Arctic and polar extrapolar interaction will be under the global climate change. Facilities such as the supercomputer, the Earth simulator, support our research activities. In our recent study, for instance, we've shown that the reproducibility of warm water transport into the Barents Sea from the North Atlantic is essential to predict the wintertime sea ice condition up to 11 months ahead in the Barents Sea and eventually in the whole Arctic Ocean.
There are lots of knowledge gaps concerning the sea ice of the Arctic Ocean, such as the sea ice thickness, sea ice dynamics, and sea ice-ocean interactions. Therefore, GMSIC is now developing a special platform that will be moved under the sea ice and measure the various kinds of data continuously and automatically. It's like an intelligent underwater drone for the Arctic Ocean. Now, we've already designed and have started building a prototype. In the near future, we believe that underwater drones will collect invariable data under the sea ice.
Thinking of future prediction about Arctic and global environmental changes, there are still many uncertainties. Therefore, we need to improve our understanding for reduction of such uncertainties. We need to collect accurate and comprehensive data, for instance in the sea ice region, permafrost area, and other data insufficient area in the Arctic. Such data and new knowledge can correct our misunderstanding of important processes for the Arctic region and support development of more accurate climate model for future prediction. Based on our results, we continue to provide useful data and knowledge regarding Arctic environmental changes toward not only scientists but also stakeholders who are interested in Arctic and global climate issues.
With the changing climate, the Mediterranean regions will undergo an increase of all kinds of extreme events, such as intense rainfall, heat waves, and rising sea levels. The Sahelian region are already affected by the consequences of the change of climate that affects soil erosions, impact on agricultural resources, drought and floods. Understanding how the environment is changing can help to find mitigated solutions for people. Hydrosciences Montpellier was founded in 1998, resulting from the merging of researchers from Montpellier University, CNRS, and from IRD. The main objective of Hydrosciences Montpellier is to quantify and predict how climate change and human activities affect water resources, mainly in the Mediterranean and tropical regions.
At Hydrosciences, we are conducting interdisciplinary research to investigate the impact of mining activities on metal contamination. We combine different chemical methods, including the analysis of metal concentration, speciation, and metal isotope ratio. Our results on the Gardon River illustrate how historic mines still contribute half a century after the closure to metal enrichment in the downstream watershed. In the mining city of Oruro, with Bolivian researchers, we highlighted the human exposure to various toxic elements such as lead, arsenic, and antimony, and we demonstrated that children were especially at risk.
In the Mediterranean region, the water demand is more and more important. Karstic aquifer may represent an important water resource for the population. The Lez Spring is the main outlet of the Lez karstic system, which supplies the city of Montpellier for water. We created the Médicis Observatory in order to characterize hydrogeological behavior in this aquifer. We work together in our Hydrosciences laboratory with hydrologists, hydrogeologists, chemists, microbiologists in order to characterize the Lez aquifer vulnerability.
Africa will lead global population growth. So preserving water resources to ensure access to safe drinking water is the most important issue. Arabian population face difficulty in water supply. The fresh water, Agien Logon near Abidjan, can be used for drinking water. Since 2050, we quantify the water flowing into and out of the Agien Logon, and we characterize the water quality in terms of nutrients. We hope that the challenge of water for the city will become the major African hydrological study.
All Mediterranean countries are affected by floods and flash floods, and this is a main natural hazard in this region. At the Hydrosciences Montpellier laboratory, we work on the topic of extreme events, starting from the precipitation to the hydrological modeling of natural watersheds, but also hydraulic modeling for urban areas. The models that we are developing are used to represent the natural processes, and then they can also be used to make future projections. There is an ongoing initiative to update the hydrological norms, in particular in West Africa, to take into account the effects of climate change. These norms are used, for example, to design reservoirs, dams, or roads.
Large rivers in Africa, like Congo River or Niger River, are a very good example of the impact of climate change because those rivers are very poorly equipped by dams and other management structures. We found a major result in the Sahel with an increasing runoff when rainfall are decreasing, which is called the Sahelian paradox. In tropical Africa, we found a decrease of groundwater reserves, which is dramatic. And in North Africa, the dams prevent many of the sediment to reach the sea, which has coastal impacts with economic issues in this area.
West Africa is a region in fast transition from the point of view of climate, demography, land use. So it is crucial to understand the underlying processes driving the water cycle. The Amakach Observatory has been set up in 4 countries over West Africa, in Mali, Senegal, Benin and Niger. The observatory is made of networks of sensors deployed into 4 countries, which document the eco-climatic gradient across the region, from the local scale, around 100 meters, to the mesoscale, some 10,000 square kilometers. We can use the Amakach networks to build and validate models that can be used for adaptation and mitigation strategies for those developing countries.
HSM is deeply involved in sustainable development related to water resources, water quality and health. It is also concerned by training younger generation of researchers to build a common future for green water. HSM works with partners in developing countries. They are involved with us in building sustainable structured researches like joint international research laboratories to have a vision on the future research and development with partnership and international programs.
Yeah, Portland State University indeed has a short and interesting history. Portland State University grew out of the educational needs in the aftermath of the Second World War, opening its door at two-year college in 1946. We established our first earth science major in 1958. In 1980, the department provided critical support during the very scientifically influential Mount St. Helens eruption. We are a small department but vibrant, with our faculties heavily involved in teaching and research, providing educational opportunity to students from many walks of life.
Here at Portland State, we are very collaborative in designing our courses and how we execute the courses, and then thinking about how we change courses to better affect student learning. And as that happens, we're allowed to bounce ideas off each other. What works, what doesn't? Hey, did this work? And how do we change this? And how do we make it better for the students in the problems that they may be having?
Oregon is in a geological frontier, and this is mainly for three aspects. We are located on the leading edge of a major tectonic plate with many active geological processes. Second, the Pacific Northwest displays an array of overlapping geotectonic regimes: subduction, rifting, hotspot setting for volcanism and tectonism, and a mid-oceanic ridge just off the coast. And finally, although mapped and studied in reconnaissance, many areas in Oregon are still poorly known.
My students and I are collaborating with the USGS, and we're mapping local faults on high-resolution topographic data. So this is LiDAR data. We're able to basically strip away the trees and look at the ground surface at really high resolution. We're mapping out more continuous fault systems than we have before, and we are finding faults that haven't previously been identified. We're finding the timing of these earthquakes on these faults. We're finding kind of lateral extent, or how long these faults are, and the magnitude of earthquakes that could occur on these fault systems.
So Portland State University Geology Department, we have a lot of different areas of research, but because we are here in Portland, the university's motto is serve the city. We have a lot of students that are focused on jobs, right? People who've been working in the workforce and have decided to come back to school, and so want that degree to do something for them. And so a lot of our research within the department is actually focused on practical applications that affect people. So the city of Portland is in a unique geologic environment in that we have a lot of hazards. We have volcanic hazards related to the Cascades, the mountains. We have earthquake hazards. We have landslide hazards. We have, in some parts of Oregon, we have tsunami hazards, right? And so there's a lot of things that, that the population cares a lot about, that the city cares a lot about, and as geologists, we can address a lot of those areas in our research, and we do.
Some of the research that we do in PSU geology is of a more fundamental nature, and that is what I do. I am studying space and planetary science, and when people think about space, they think about telescopes and astronomy. But actually at the Cascadia Meteorite Laboratory here, that's housed in the Geology Department, we are all about studying space rocks, meteorites. And we have the largest collection of meteorites in the Pacific Northwest. It's really a good thing to have that, because you can't go out into space to see the outcrops. You have to have the outcrops come to you. And we are able to do that here in geology. So at Portland State University, we do fundamental research in water as well. This is in relation to climate change, partly, looking at western United States glaciers. At Portland State University, we're very close to Mount Hood, which has a glacier on it. This is a glacier that you can visit
in one day, right? We can drive to that glacier and back to Portland in one day, which is really unique for a university. So looking at glaciers on Mount Hood and other mountains to understand climate change. In addition, looking at paleoclimate, so climate in the deep past, in the geologic past, and understanding how that's changed both in the Northwest and in other parts of the world.
So the student experience in the geology department is varied depending on the type of student that comes to us from different places. So we'll have the traditional students that come from a two-year community college situation. We have students who are returning to continue in a new career, and we also have senior students who are lifelong learners. We give them opportunities for a variety of classes, both hybrid and online, and we also have a two-year program that allows us to give them a number of entry points, either freshman year or the junior year, to accommodate these different learners.
This region is a fantastic classroom. So we have students learning here at PSU, but we get them out in the field. That's from our 200 series. These are just undergrads, non-majors. Our majors are out there in almost every course, and our graduate students. So it's a phenomenal opportunity for students to learn about active processes and to go out and see those processes, to map them and to understand them. It's really a unique environment to learn in.
Yeah, I think we have a bright future, and it's basically because geosciences are really so important for understanding what's going on around us with climate change, with water resources. So I see a growth in the department and this interdisciplinary where we basically solve problems together from different disciplines.
As you know by now, our special correspondent Heidi is out and about asking you the question of the day. So Heidi, what is it today?
Thanks, Stephen. I'm here in the poster hall today asking a range of scientists, what is your one piece of career advice for early career scientists in the earth and space sciences?
My one best piece of advice for early career scientists is to not underestimate the power of networking. Use your contacts, use who you know, because that can take you very far in this field.
One piece of advice I would give would be to get out, meet people, go see their posters, interact with the community, get involved.
My one piece of advice for early career scientists would be staying curious and publishing early.
My one piece of advice would be to get into the projects that you're really interested in and meet other people working in related areas and start publishing early.
I would absolutely say never say no to opportunity. Always look for, possible things to do, internships, getting to meet people, and really taking advantage of all the opportunities that are out there.
My one piece of advice for early career scientists would be to try out working in different sorts of locations and different things to see what you like, to see what you experience, and whether or not you stay in your scientific discipline or go into other areas, that experience will be really enriching.
The one piece of career advice that I would give an early career scientist would be to find something that you're passionate about and to merge that with your research interest so that at the end of the day, when it all is said and done, you feel like you're giving back to the community because you're doing something that you're really passionate about and that you're really good at because you spent your career actually learning about that from a research perspective.
The biggest challenge that we're going to face in the coming century is the growing populations. And in geophysics, we can't help solve all of the problems that stem from that, but there are a few that we can. The geophysics department at Colorado School of Mines was a leader in creating the geophysics curriculum and education and research in the past century. And we're really trying to take a leadership role in understanding what that needs to look like in the 21st century. So in particular, energy, water, climate, and then the related system of food. These are things that we, in geophysics, can help the world solve.
We have done significant changes to our program in the past few years. Quite dramatic, actually, including into how we teach our students and what we teach them.
It's a very exciting time to be at Mines with all these new developments.
Also, it's a really awesome place to live.
We're sitting here right at the foot of the Rocky Mountains. We can see geologic change right here outside of our door. I couldn't think of a better place to be.
A lot of the work that we do involves being outside, collecting measurements at a site of interest with new and exciting instrumentation that perhaps people haven't been thinking about before.
We've created what we call a Cafetar Geophysical Laboratory, and we've buried geophysical targets in our commons. So we know exactly where they are, and we can test out our new techniques to see if we can actually image and see these buried targets.
We are entering the era of big data in geophysics, quite powerful change into how we conduct our activities and how we shape the educational programs, what we teach our students and why we teach them to do certain things.
Some of these new deep learning mechanisms are allowing us to explore more subtle or weak or nuanced physics that we didn't see before.
We cannot separate theoretical understanding from data acquisition and data processing. And we have to bring all of these together, and we have acquisition that satisfies theoretical requirements and is exploited in real time to feed back into acquisition, to feed back into interpretation, and create this virtuous circle that gives us insight into the subsurface.
In places where physics is a bit blurry, a bit fuzzy, machine learning comes in to help us to understand that part of the physics more. So it's a very great advantage in that sense.
We're imparting domain knowledge in our students along with the right computational skills in order to utilize these new algorithms for solving these problems.
So one particularly cool technology we have to convey our geophysical findings is virtual reality. So we've been working to build a software base that allows us to integrate all of our geophysical data with other intuitive spatial references in one common rendering environment that we can immerse people in fully in virtual reality.
These technologies, the growth in these technologies is really creating a renaissance in the geosciences, and our students need to be prepared for that. At the graduate level, we're introducing 2 new degree programs. One is in humanitarian geophysics.
One of the things that we're really excited about here is how we can use geophysics as an applied science in order to address some of these very important questions of community development challenges around the world. And so if we go out and deploy electromagnetic surveys or resistivity surveys or seismic surveys, we can collect a variety of different geophysical data types that can be integrated into a single interpretation that then allows us to identify potential new locations for groundwater. One of the really challenging parts of doing humanitarian geophysics is largely access to geophysical instrumentation. So we have a couple projects that are going on looking to develop resistivity meters, low-cost seismometers that can actually be employed in groundwater investigations to really lower the barrier to entry and allow a much wider scale application of this technology throughout the developing world.
We're also putting a lot of emphasis on hydrology and hydrogeophysics, and we have a new program in hydrogeophysics that we're just launching.
One of the things that's really changing the way we think about hydrogeologic processes is airborne measurements, which have been around in mining for ages, but not so much in hydro. And so we can now fly and see down hundreds of meters into the earth, and that gives us a way to take a look at what the bottom boundary might look like for some of the numerical models we make. We're training people that really are at those interfaces that understand hydrogeologic and hydrologic problems, but then know how to solve those problems. So for me as a teacher, it's really exciting to be part of a program that really integrates those two things together.
Geophysics at the Colorado School of Mines is
adapting to the way in which the world functions today.
Geophysics at the Colorado School of Mines is preparing to change the world.
Astronomers for generations have been looking at the sky, and of course we've done multi-wavelength, multi-energy astronomy. So we look in the optical, or we look in the infrared or the radio, or we can go to higher energies and look in the X-rays and gamma rays.
However, once you reach wavelengths as small as high energy gamma rays, the sky is not transparent, it's opaque to light. So we know that there is at least 20% of the universe we have never seen.
And so multi-messenger astronomy, in particular neutrinos, using neutrinos instead of light or photons, has the promise of being able to look at energies well beyond what we can do optically.
Neutrino astrophysics is a very exciting field because neutrinos are so numerous out there and they play an essential role in many phenomena like supernova explosions or the formation of galaxies or the life, birth and death of stars.
The neutrinos we see today come from sources going back to the beginning of the universe and come from throughout space.
Yet they are among the hardest to catch particles. And this poses the greatest challenge to an experiment that is actually searching for astrophysical neutrinos.
EarthCube was the first experiment of a cubic kilometer in size that was able to see a diffuse astrophysical flux of neutrinos.
Nobody had ever built a kilometer cube detector, never mind a neutrino detector. And of course the motivation was to prove that it was large enough to see the cosmos in high energy neutrinos. And we indeed proved this was possible. So how did we do it? Well, it's interesting, the detector was already there. It's a block of ice, highly transparent. Blue light travels 100 meters to more than 200 meters throughout its volume. So it's what physicists call an ideal Cherenkov medium. It's shielded by 1.5 kilometers of South Pole ice, shielded from radiation at the surface and cosmic rays. So all we had to do was instrument it.
The construction of EarthCube is a huge challenge, and it's a many-year effort. So, I mean, the first articles that were written about the possibility of EarthCube were, back in late 80s, early 90s, and we started construction in earnest in like 2003, 2004. And once you get into the construction mode, it's all about schedule. And in our case, the bottleneck was installation of instrumentation deep in the ice at the South Pole.
We filled this kilometer cube of natural Antarctic ice with 5,160 photosensors, which are basically 10-inch photomultipliers, which you buy in Japan. The real problem was to put them in the ice and to figure out how to read them out. And so we solved that problem. It took a while, but EarthCube is ticking like a Swiss watch right now.
I went to Po twice as a grad student to help with the construction of the detector, and I went last year to install some scintillator panels in a R&D project for future upgrades. Every task has a risk, which I think is amplified by the fact that the environment is unique. It is quite high, but it's very cold, very dry, and very isolated. So even simple hardware installation can be challenging.
Very challenging, very difficult, a lot of hard work, a lot of pressure, and we had fun.
The big question now is where and how are neutrinos produced?
There is a type of event that we are looking for. It's called the glacial resonance. It sits at a certain energy where interactions are more likely than at other energies. So we actually should find it. But you never know. I mean, it might not come. And if it doesn't come, that's also fine for us, because then it's a new opportunity to rethink models and make new models and open new windows to eventually new physics. I mean, that's always what gets people excited, me as well. The possibility that there might be something hiding in the data that opens the window for new physics.
There's the science, there's the ultimate thing that you want to do, the knowledge you want to bring to the scientific community, and then there's the day-to-day excitement of what you're doing. And it's the kind of thing you can't do by yourself, in a lab down in the basement. This is something where you need a dedicated group of people with a common goal and interest to work together collaboratively to do science that otherwise you couldn't do.
In the Geophysics department at GFZ Potsdam, the German National Center for Geosciences Research, we cover a wide range of geophysical observations which aim to study the dynamic behavior of the solid Earth. We also stretch our research to magnetospheric physics in order to include solar winds and radiation. We have no direct window into the interior of the Earth. Therefore, we study with geophysics the interior of the Earth indirectly from Earth's surface or from space to provide further evidence of the geodynamic behavior of the solid Earth. In addition to the research-related objectives that we pursue, for instance, global tectonics, geohazards or georesources-related research, we also provide different community services. These encompass the provision of the Geomagnetic Index, internationally operating geophysical instrument pool in Potsdam, GIP, and it also includes the Geophone network that delivers rapid earthquake responses.
GFZ built the Geophone system to observe earthquake activity worldwide, and it consists of 90 seismic stations which operate in all kinds of environments, from polar regions to jungles to deserts. And each of these stations can record minute ground motions so that it's sensitive to earthquakes on the other side of the planet. And we combine the data from all these stations to find where earthquakes happen. We're able to do this within a few minutes of the earthquakes happening anywhere in the world for moderate and large earthquakes. Seismology is a cooperative science. We rely on the hosts of our stations to look after them together with us. And only by combining data sets from many networks, we are able to observe seismic ruptures in detail, find crisp images of basically in real time. Many earthquake centers and tsunami warning centers worldwide make use of this facility for their warning procedures. The Alps are a spectacular place to study mountain building, as they're still actively evolving today due to the northward push of Africa into Eurasia. And in Alparray, 18 European countries came together to operate a very dense network across the Alps and also the surrounding regions, and to be able to image the structure beneath the Alps in great detail. GFZ's contribution is to build an even denser network across a particular place in the Alps that is very enigmatic, because there it seems that the polarity of subduction is changing direction. We have teamed up with our partner institutes in Italy and Austria to put stations at 15-kilometer distance. So with this dense network, we will reach a level of resolution that we are able to link faults at the surface to the deformation in the upper mantle and lower crust. There is a huge gap still in our networks in the oceans, because dedicated undersea cables are just incredibly expensive to maintain. But there are hundreds of thousands of kilometers of communication cables already present, which are currently completely unused for this purpose, but offering access to communication and to power. We are currently engaged in discussions with operators of these cables and equipment manufacturers to see if we can add sensors to these cables and therefore allow observation also on the seafloor.
I'm the leader of the Helmholtz group Crystals, which is embedded in the GFZ's geodynamic modeling section. In that section we model large-scale geodynamic processes like mantle convection and plumes, but also rifting and subduction and earthquake cycles and tsunamis. In my group we focus on continental rift and rifted margins, and we combine numerical simulations with available geological and geophysical datasets. To this aim we work with groups at GFZ and the University of Potsdam, and of course with international collaborations, for instance from Australia, Italy and the US. In future, we will also look at the largest rift system, the East African one, and we will answer questions like how do tectonic processes interact with migration of volatiles and melts. The increasing power of supercomputers will help us answering these questions, because it will allow 3D high-resolution numerical modeling across the scales. Measurements have shown that rifts release large amounts of CO2 because they connect the huge carbon reservoir in Earth's mantle to the surface and to the atmosphere. We analyzed the extent of rift systems since the breakup of Pangaea during the last 200 million years, and we found that the global rift length evolution matches the CO2 history of the atmosphere. This shows that tectonic processes are not only responsible for shaping our continents, but also have strong impact on long-term climate changes.
The Earth magnetic field is generated in the outer core due to moving liquid iron, and it reaches out several Earth radii into space, where it protects us from solar and cosmic particle radiation. Some of these particles are trapped in the magnetosphere and form the Van Allen radiation belt. This is a region which is dangerous to satellites, which we depend on in our daily life. We at GFZ want to understand the evolution of the geomagnetic field in short and long time scales, and we lie special focus on the ionosphere and sources in the magnetosphere to best quantify the state of the space environment. This space environment is very harmful to satellites our society is relying on, and it is also responsible for interruptions in trans-ionospheric emissions like GPS.
The Russian authorities operate a real-time seismological monitoring system with stations at different volcanoes in Kamchatka. But to investigate the detailed structure of a volcanic system and the processes in its interior requires dedicated experiments with many stations focused in a smaller region. To investigate the Kluchevskoye volcanic group, the GFZ, together with French and Russian partners, conducted a field experiment and installed 83 temporary seismic stations around the 4,700 meter high Mount Kluchevskoye. The Kluchevskoye volcanic group comprises 13 volcanoes and is one of the most active places in the world. To access these sites with 40 kilograms of equipment per station, we had basically only one option: to use a helicopter. With drones, we bridge a gap between surface and remote sensing observations with satellites. One speciality is to go close to the summit of an erupting volcano independently of scheduled satellite flights and without risking lives. The precise deformation and temperature measurements reveal precursors and dynamics that has been completely undiscovered a few years ago.
We have sinkhole recognition program. Sinkholes are circular to elliptic structures at Earth's surface, which can lead to collapse if soluble rocks in the subsurface bring out cavities, and these cavities collapse if the strength of the overburden is mechanically not any longer stable. This may pose a severe hazard, especially in urban areas. And to study this, we want to look at precursor phenomena, to study if there are interactions of processes that we can depict easily and understand, and if there are small variations that we can feed in those systems for early recognition. To summarize the future research goals, firstly, we would like to use the full observational potential that we have to close the gap between surface and deeper Earth observations. This may help geodynamic studies, but also resources-related questions. Secondly, we would like to include magnetospheric physics. This will help broadening our geohazard spectrum towards space weather. And then thirdly, we may count on geohazards, which means to deliver rapid responses, hazard maps and also risk dynamics to give some decision potential for preparedness and early warning.
I'm here with Tim Van Emmerich, and I want you to tell us a little bit about your role at AGU and what it is that you do.
Yeah, sure. Well, hi Heidi. Very nice to meet you and
Likewise.
to talk about what we do here at AGU this fall meeting. I'm actually currently an early career member of the AGU Council, next to my normal job as a scientist back home. I'm a hydrologist by training. I've been very active in the hydrology section here at AGU. But right now I try to organize basically the early career scientists and the students all together here at AGU through all kinds of capacity building initiatives, trying to connect all the early career scientists and students and try to make sure that they learn the right skills to develop their careers as scientists in the future.
Can you give me a few examples of what those skills look like, or what sort of opportunities you've been engaging in here at AGU that early career scientists like myself could get engaged in?
Yeah, well, I really believe that the new scientist needs a whole palette of different skills. It's not only about writing your papers for the high impact journals, but it's also about science communications in very different forms. So communicating with different audiences, not only with your peers, however, of course, that's extremely important for your network and for building towards great science and great collaborative science. But there's more people out there. There's the general audience, there's a lot of stakeholders normally involved in your projects, etc. And the conventional ways of communicating our science normally don't work per se. And one of the things that we do here, for example, is show scientists that they can use, for example, poetry to communicate their science.
Really?
Yeah. Yesterday we had the Rhyme Your Research science poetry workshop.
Fun.
Yeah, where we sort of demonstrated how poetry can be used as an alternative way to communicate science. If you ask people to write a poem, that the first thing that they do is try to rhyme, which is fine.
I guess I'm like everyone else then.
Yeah, well, I always say if it rhymes, it's true. So that's my science poetry philosophy in a way.
Very cool. That's fantastic.
Yeah.
And do you share those anywhere? Those poems here at AGU?
Yeah. Well, we are posting them right now on our Twitter feed.
Is there a hashtag associated with that at all?
Well, we just use the general AGU 18 hashtag.
Okay.
For this to reach as many people at AGU as possible.
So if you also want to hear about the latest science, but also see some poetry about that very same science, hashtag AGU 18.
Exactly.
Awesome.
I understand that you work a lot with stakeholders, right?
I do.
Can you maybe tell me a little bit more about that?
Yeah. So I took advantage of many of the opportunities at AGU to build skills in communication when I was a PhD student, and even as an undergrad. I've been coming to AGU for more years than I'd like to admit. And slowly through doing my science, I really realized that the way that I would have an impact was through trying to figure out how it is to bring climate science to decision makers and end users, right? We produce an amazing amount of science here at AGU, right? I think it's something like 1,800 sessions and tens of thousands of oral presentations. And so I focus on climate. My background is in climate research, and now I really focus on delivering that climate information to the people we really want using it.
So is that also the messages that you sort of that you convey to your students and to the new generation, or to the science that you train to do better science communication?
Yeah, I think so much of it is just giving people a platform and giving them the confidence to start talking about why climate matters to them and how they feel it personally and how that maps on to their job function, whether you're in the private sector, the public sector, or an early career scientist coming up through the ranks.
Yeah.
So thank you so much for the great conversation.
Thank you, Heidi.
And for all the work that you do.
Yeah, thank you. You too.
Thank you. Hi, I'm here with Raj Pandya, Director of Thriving Earth Exchange. Welcome.
Thank you.
Thank you for having this conversation.
I'm excited about it. Thanks for inviting me.
So you're the Director of Thriving Earth Exchange. Can you tell us a little bit more about that?
Yeah, it's actually pretty simple. We sit down with community leaders, understand what their priorities are, where they want to go, and then we try to find ways that Earth and space science can help them get there. And then we reach out to AGU members and other scientists and ask if they want to volunteer to be partners on that project. Then we do everything we can to support that team working together to make a real concrete impact in the places those communities are.
Fantastic. Can you give me a concrete example of who a community member is that you would engage through Thriving Earth Exchange?
So one example was in the city of New Orleans. There was a community neighborhood leader who was concerned about flooding in her neighborhood, and she wanted to collect data to show that flooding was a real threat to that neighborhood. And the data she collected was not only used that data with the city to help them expand their redevelopment program to include her neighborhood. It also ended up being contributed to the local NWS office to help them do a better job of hydrological forecasting.
Fantastic. And so Thriving Earth Exchange, were you part of that connection? So between the local actor and say NWS, you serve as the conduit to make that connection?
Right, and we helped find the scientist who had the right kind of technical expertise, but also the right kind of social and collaborative skills to be a good partner with that community effort. Another example is a town in New Berlin, Maryland. They bought a chicken processing plant and they wanted to turn it into a park, and they needed some help understanding what kind of contaminants they needed to be aware of and how they might remediate them. So we helped them connect with a scientist who could help them map out a remediation strategy. And they actually estimated that saved them about $5 million through consultants that were trying to push more than they needed.
Fantastic. So can you tell us who those scientists are, maybe not by name, but sort of what types of disciplines you're engaging in Thriving Earth Exchange to help with these challenges?
Great question. It's almost every kind of discipline you can imagine. You know, the technical expertise is important, but what's also important is the fact that scientists bring a whole skill set around how you ask questions, how you investigate issues, how you collect data. They know how to navigate these systems. They know how to find interesting and relevant information. They know how to read scientific papers. So sometimes the discipline, it's the broad sort of understanding of scientific processes that they bring to the table, even as much as their specific disciplinary expertise.
Great. And so for those of us at AGU, how is it that we get involved in Thriving Earth Exchange or start making these connections between the research we do and communities that have these questions?
So I'd give you two answers.
Okay.
The first is you can just check out our website, thrivingearthexchange.org, and you can look for projects that are going on that you might want to get involved in. But even more profoundly, I would encourage folks to talk to their neighbors, to talk to people they know, to find out what kind of issues are going on in their community, and to play a sort of how could I help game, or how could my science be relevant game, and to think about their science broadly, not just, you know, I'm an X-ray crystallographer, but I'm a scientist. I think one of the most profound things we can do to help connect is actually work in the places we live, work, and play, and try to get involved in local issues and try to bring the technical skills that we have to bear on those local issues, not in a telling people what to do way, but in a being a partner in figuring out what we want to do kind of way.
Right. And do you know of any resources that sort of help facilitate that interaction? You know, Thriving Earth Exchange is one, but I can imagine for many of us, having that conversation or initiating that conversation outside of our expertise can be difficult to start, or to sort of cue into that, oh, that's a question I can either help answer or I can help connect the pieces or the dots for someone to find those resources.
Yeah, I think, so good places to start might be local boundary organizations. You obviously know about them because you're one. But you know, there's Sea Grant programs, there's RISAs, there's climate service centers. Those are all entrees. We've had really good luck connecting with like the National League of Cities or the International County Managers Association, and they can help us. And that's one of the things AGU as an organization can do. We can build those organizational connections that allow our members to reach out to us and say, hey, I'm interested. Is there a local connection? Is there a local partner you can introduce me to? And we can often do that. I actually think this is the cusp or the beginning of a really profound change in the way we think about science and its role in society. And I think it's sort of an awakening to a sense of not just doing science for the sake of knowledge, which is wonderful, but actually doing science to help build this better world we want to build, and doing it with humility and grace and in partnership, and drawing on a whole repertoire of skills, not just scientific skills, but community knowledge, community wisdom. And I think this kind of locally engaged, meaningful work is how we're going to figure out how we live sustainably, how we live on this planet in an equitable way.
Well, fantastic. Thank you for all your work and for Thriving Earth Exchange, and for being so committed to all the science to action work that's underway this week at AGU.
I'm afraid that's it for today, but don't worry, we'll be back each and every day with yet more exclusive material. In the meantime, you can watch the show all over the Convention Centre, in your hotel room and online, as well as on the AGU 4Meeting app. And don't forget to keep up with all the very latest developments and get in touch via the web. So until tomorrow, when we'll be talking to the Executive Director of the AGU, Chris McEntee, it's goodbye.